In this video, we will learn to do some multivariate analytics when all the variables are quantitative in nature. So here we have some data on 25 patients. We have the height, the weight, BMI, age, systolic and diastolic pressures, glucose rating, rest pulse rate, and health rating. So all these variables are quantitative in nature. The first The first column is really not data, it's just entity labels. Okay, so the first thing we will do is do side-by-side box and whisker charts. So we select the data and we go insert, recommended charts, all charts, box and whisker. There. So this is just to show you that Excel allows us to do side-by-side box and whisker charts for comparison purposes. Although in this example, it's not a good idea to put all these side by side because these variables are not of the same units. So we really cannot compare variables of different units by putting them side by side. So in this example, systolic and diastolic pressures are the only two variables that share the same units. So we should insert box and whisker charts for those two for comparison purposes. There. So from here we can say that systolic pressure mean is higher than diastolic pressure mean. The interquartile range for systolic is greater than the interquartile range for diastolic pressure, and so on. So we can tell a story by comparing two variables of the same units. Next, we will learn how to find relationships between these variables. So the first thing we'll do is create a correlation matrix, a correlation matrix. For that, we will need the data analysis pack. So we will click on data, and next we will click on data analysis, and we will select correlation, correlation. Okay. And we want to select the input range. So we will select C2 K27 labels in the first row. And let's put the output over here. There we have the correlation matrix. So to get a visual effect of which correlations are higher or lower, we can create a heat map by doing conditional formatting. So we select all the correlation values, we click on conditional formatting, and we can select any one of these, and we have a correlation heat map. So we can easily see that this is a very high negative correlation. So the negative correlations we can see in reds, and positive correlations we can see in greens, and medium in yellows. So this one stands out. BMI and health rating are highly negatively correlated. Next, we want to learn how to perform regression analysis. We can do several simple linear analyses involving one independent variable and one dependent variable. And then we will learn how to do multiple regression analysis with more than one independent variable and one dependent variable. So let's first learn how to do some simple regressions. We will do a simple regression on height and weight. So before we actually run the regression, it is a good idea to create a scatter plot. So insert a scatter plot. There's a scatter plot. So just by looking at the scatter plot, we get a sense of the type of relationship. Let's recalibrate the x-axis so that the starting value is not 0, but say 55. So the scatter plot looks a lot better. We can select any one of these points and add the trend line and also display the equation on chart. So that's the equation on chart. And we can select a different type of display. So just by looking at this chart, we can say a few things about the relationship between height and weight. We can say that the relationship is positive. We can say that as height increases by 1 unit, weight increases on an average by 3.5462 units or pounds. But is the relationship strong? What's the R square value? Is it statistically significant? For that, we will have to run regression analysis. And for regression analysis, we will use the data analysis stack. So we click on data, we click on data analysis, we select regression. Okay. We select the Y range, which is the dependent variable weight. We select the X range, which is the independent variable, in our case, height. We select the output range, let's say here. Okay, so we see a regression output. So we see lots of numbers on this display. So what are the numbers we are interested in? The R square value, the significance value or the P value, and these coefficients. So these coefficient values we've already seen in the equation here. The R square value has a nice interpretation. Here the R square value is 0.3516, which means 35.16% of the variance in weight is explained by height. About 65% is not explained by height. That 65% might be explained by other factors that we may not have considered here. The significance value, 0.001, what does that mean? Because it is less than 0.05, we can say that this relationship is statistically significant. So this was simple regression involving one independent and one dependent variable. So there are so many possible simple regressions that we can perform because there are so many possible pairs of variables. Let's do one more, BMI versus health rating. So health rating is our dependent variable and BMI is our independent variable. So first thing to do is create a scatter plot. So insert a scatter plot. Let's recalibrate the x-axis. Starting value can be 15. Let's put the trend line, add trend line. Let's display the equation on chart. Display the equation on chart. Let's change the style. Okay. So just by looking at the chart, we can say that the relationship between BMI value and health rating is negative. And the relationship looks very strong because all the scatter points are very close to the trend line. And by looking at the equation, we can say that as the BMI value increases by 1 unit, the health rating decreases by 5.7 units. What's the R square value? Is this statistically significant? To answer those questions, we will have to run the regression analysis. So let's do that. We need data analysis pack. So we click on data. We click on data analysis. We select regression. Input Y range is health rating. Input X range is BMI value. Let's get the output in M3. Okay. There we have a regression output. So what are the important things to look at? The R square value, the P value or the significance value, and the coefficients. So the coefficients we have already seen here in this equation. R square value is a new thing. 88.4% is a very high R square value. This is saying that 88.4% of variation in health rating can be attributed to BMI. Is the relationship significant? This value is 2.96 times 10 to the power of minus 12, which is extremely small value. It is definitely less than 0.05. Therefore, we can say that this relationship is statistically very significant. So we can do simple linear regression on age and health rating, systolic pressure and health rating, diastolic pressure and health rating, glucose and health rating, rest pulse rate and health rating. Let's do this one. First, we do the scatter plot. So on this scatter plot, we don't see a very obvious positive or negative relationship. The trend line does show that it is negative, but it's not a very pronounced negative. And the points are scattered quite far from the trend line, which means the relationship is not very strong. What's the R square value and is the model significant? For that, we will run the regression analysis. So we will click on data, data analysis, regression, and we've selected the Y range and the X range. And let's get the output in M3. There's a regression output. The R square value is very small, 0.02. The significance value is not significant, 0.437. It's much bigger than 0.05. So this is not a significant relationship. So unless we did the scatter plot, unless we ran the regression model, we would never be able to know that this variable is not related to health rating. We can also do some multiple regression involving two or more independent variables. If we have two independent variables, like in this example, we cannot do a scatter plot because we will have to do a 3D scatter plot. And Excel cannot handle 3D scatter plots. But in Excel, we can create a bubble chart, insert bubble chart. So that's the bubble chart. Here, on the x-axis, we have the BMI value. On the y-axis, we have the systolic pressure value. And the diameter of these bubbles are proportional to the health rating. So without looking at the diameter of the bubbles, we can tell what's the relationship between BMI value and systolic pressure. It is positive. Now, if you look at the bubble sizes, then we see that as BMI value increases, the diameters are decreasing, which means as the BMI value is increasing, the health is decreasing. So there's a negative relationship. Similarly, as the systolic pressure is increasing, the diameters are decreasing, which means there's a negative relationship between systolic and health rating. How strong is the relationship? For that, we will have to do multiple linear regression analysis involving two independent variables. So we click on data, data analysis, regression. Y range is health rating. X range includes two columns of data. So let's get the output over here. Okay. So that's the regression output. Because we had two independent variables, we have an extra coefficient. So we have three coefficients here. R square value is 0.907. Significance, very significant. So BMI alone contributed to 88% of the variation in health rating. BMI and systolic combined can explain 90.7% of the variation in health rating. We can do more complex multivariate analysis by having six independent variables. So we can do multivariate analysis on this much data at one time. We could do all, but then height and weight are already included in BMI, so it does not make sense to have height and weight and BMI. So we cannot do any bubble chart, we cannot do scatter plot. So let's do regression analysis right away. So data analysis, regression, Y range is health rating, and X range is BMI through rest pulse rate. And let's get the output here. Okay, so that's the regression output. Since we have six independent variables, we got seven coefficients, one for the y-intercept and six for each of the six independent variables. The R-square value is 0.911, which is very good, and the model is very significant. Now, individually, BMI is significant. The other five are not significant because the other five are not less than 0.05. But the overall model is significant. So that's how we do multivariate analysis when all the variables are quantitative in nature.